Now we will expand a given complex valued function about a point in terms of power series. Such an expansion is called as a Taylor series. We have two types of series. One is called as the Taylor series and the other one is called as the Lorentz series. There is a minute difference between these two. These two series gives a power series expansion of the given function f of z about a particular point. This is the statement of the Taylor series. If the function f of z is analytic at all points inside a contour C with center z0 and radius r, then we can expand f of z in terms of f of z0 plus f dash of z0 by factorial 1 into z minus z0 plus f double dash of z0 by factorial 2 into z minus z0 whole square plus so on. Okay. So in this case, this right hand side power series converges to f of z, where z is a point inside the contour mod z minus z0 less than r. This expansion is called as the Taylor series expansion. I am not going to discuss the proof of this. This you can see it in any standard textbooks. But we will see certain examples how to expand a function f of z about a particular point. Okay. And this function looks similar to the Taylor series expansion of a real valued function. And as in the case of the real valued function, when I take z0, namely the point about which you find the power series, if that is 0, then the Taylor series is also called as the Maclaurin's series. That is also called as the Maclaurin's series. So this is the, you have to remember the statement. This is the property of this Taylor series. You have to remember the expansion, use it appropriately in the problem. Now, as a first example, we will expand f of z about the point z is equal to 1. So your power series expansion contains terms of the form z minus 1, z minus 1 the whole squared and so on. So the Taylor series involves the derivatives, also it also involves the derivatives f dash of z, f double dash of z and so on. So now what I do is I calculate the nth derivative of 1 by z, which is minus 1 whole power n into factorial n by z power n plus 1. When I take n is equal to 1, I will have f dash of z, as f dash of z will become minus 1 by z squared, because minus 1 whole power 1 will become minus 1, factorial 1 is 1, z power 1 plus 1 will give you z squared. When I substitute n is equal to 2, I will have the expansion, I will have the value of f double dash of z. Now, I write the Taylor series expansion. F of z is equal to f of z0 plus f dash of z0 by factorial 1 into z minus z0 plus f double dash of z0 by factorial 2 into z minus z0 the whole square plus so on. Here we have taken z0 is equal to 1 because the expansion is required in terms of z is equal to 1. So I have to replace z0 with 1. Okay. And now I will have z minus 1 here, z minus 1 the whole square, similarly z minus 1 whole power n, and f dash of 1, f double dash of 1 and so on. So when I substitute the value of z is equal to 1 in f1 fn of a, you can see here fn of z, this was minus 1 whole power n factorial n by z power n plus 1. Okay, so now when I substitute n is equal to 1, okay, when I substitute n is equal to 1, I will have minus 1 whole power n. When I substitute n is equal to 1, I will have f dash of z. This will be minus 1, oh sorry, not f dash of not okay, not f dash of z. I require fn of 1. Fn of 1 will be minus 1 whole power n by by into factorial n by 1 power n plus 1. So whatever be the values, because here it is going to be positive values, so this will be 1. Okay, so I will have minus 1 whole power n by factorial 1. When I substitute n is equal to 1, I will have minus 1. When I substitute n is equal to 2, I will have minus 1 the whole squared, which will become plus 1. I will have factorial 2, which is written here, factorial 2, and this factorial 2 is there, z minus 1 the whole square. So here z factorial 2 gets cancelled, and here in the next term factorial 3 gets cancelled. Similarly factorial 4 gets cancelled in the next term, and so on. So when you write it in a summation notation, you can write this as minus 1 whole power n z minus 1 whole power n. This will be the Taylor series expansion of the function f of z is equal to 1 by z about the point z is equal to 1. If I want, I can also expand across the point z is equal to 2. So accordingly, I have to just suitably adjust the formula and find the expansion of f of z about the point z is equal to 2. So this is the first example of expanding a given function using the Taylor series. Now I take the second example as an hyperbolic function. F of z is equal to sin hz, and you know that sin hz is e power z minus e power minus z by 2, and we require this cos hz. So I will write the value of cos hz in terms of exponential function as e power z plus e power minus z by 2. Because when I differentiate sin hz, I will have cos hz. Because when you differentiate e power z, you will have e power z. When you differentiate e power minus z, you will have minus e power minus z. Already you have a minus, so minus into minus will become plus. So in this case, when you differentiate sin hz, you will have cos hz, which we will be using it in fn of z. And similarly, when I differentiate cos hz, I will have sin hz, because e power minus z, when you differentiate, you will have minus e power minus z. So differential of sin hz will become, differential of cos hz will become sin hz. So I have written the hyperbolic function sin hz and cos hz in terms of the exponential functions, and that is been given here. Differential of sin hz is cos hz, and differential of cos hz is sin hz. And similarly, cos h pi I is minus 1 and sin h pi I is equal to 0. This we can easily see. What is this cos h pi I? Cos h pi I is e power pi I plus e power minus pi I whole divided by 2. So this will be 1 by 2 times, okay, this will be cos pi I, cos pi plus I sin pi, okay, and e power minus pi I will be cos pi minus I sin pi, okay, minus I sin pi and plus I sin pi gets cancels, giving you cos pi, and you know that cos pi is equal to minus 1. Similarly, when you expand sin h pi, you will have e power pi I minus e power minus pi I whole divided by 2. I can write this as 1 by 2 times cos pi plus I sin pi minus cos pi plus I sin pi. Okay, minus cos pi gets cancelled, and you know sin pi is 0, so this part will be 0. So you remember the value of cos h pi I, which is minus 1, and sin h pi I, which is 0. Now I have given the expansion, Taylor series expansion, general expansion. Instead of this z0, I have to expand it across z is equal to pi I. Okay. So now I have just substituted z0 is equal to pi I. Okay. Now I will have alternatively sin h pi I. F of z is sin h z. So f of I pi will be sin h I pi, which will be 0. And when I differentiate sin h pi, I will have differentiate sin h z, I will have cos h z. And we know that cos h pi I is minus 1. I have suitably written the values of f dash of I pi, f double dash of pi I, so on, to give an expansion of f of z about the point z is equal to pi I. And when I use the summation notation, I will have the expansion of sin h z as summation k is equal to 0 to infinity minus 1 into z minus I pi whole power 2k plus 1 whole divided by 2k plus 1 factorial. You can see here z minus I pi whole squared is missing, z minus I pi whole power 4 is missing, or in other words z minus I pi whole power k, where k is even, is missing. So in order to get only the odd powers of z minus pi, I have made the index to run from 0 to infinity, and I have replaced n with 2k plus 1, which is the representation of an odd number when k is greater than or equal to 0. So this gives the summation notation of the Taylor series of the function f of z is equal to sin h z. The greatest disadvantage in the Taylor series expansion is that you cannot expand f of z about the point of singularity. About the point of singularity, you cannot expand. If you could remember, in example 1, we took the Taylor series expansion of f of z is equal to 1 by z, but I had restricted that z should be non-zero. Okay, when z is equal to 0, this will not be analytic. So in this case, at the point of singularity, you will find it difficult, or you cannot expand the given function using the Taylor series. Okay, this is the greatest disadvantage. But to overcome this disadvantage, somehow you can expand f of z in positive terms as well as the negative terms of z. That will give you a new type of series called as the Lorentz series. So as an example for this, what I have done is, I have taken a function f of z is equal to 1 plus 2z by z squared plus z cube. And when you look at this denominator, when I remove this z squared, I will have 1 plus z into z squared in the denominator. And z squared is equal to 0 will give you z is equal to 0. So in this case, f of z has a singularity at z is equal to 0. Okay. But now what I do is, I suitably adjust the function f of z and try to expand f of z using the known series, namely using exponential series or binomial series or logarithmic series or any expansion that is known. I can expand this by suitably adjusting the terms. So now what I do is I remove this 1 by z squared and rewrite 1 plus 2z by 1 plus z as 2 minus 1 by 2 1 plus 2z. So when I simplify this, I will have 1 plus 2z by 1 plus z. This you can see here, 2 plus 4z. Oh, I think I have made a mistake here. 2 minus 1 by 1, oh sorry, it has to be 1 plus z, not 1 plus 2z. Okay, 1 plus z. So when I do it, I will have 2 plus 2z, okay, minus 1 by 1 plus z. This will be 1 plus 2z by 1 plus z. Okay, so in this case I will write this term 1 plus z, sorry, 1 plus 2z by 1 plus z as 2 minus 1 by 1 plus z. And when I use the expansion of 1 by z, so in this case it is not 1 plus 2z, it is 1 by z. So when I use the expansion, of 1 plus 1 by 1 plus z, I will have 1 minus z plus z squared minus so on. And when I simplify this, I will have the expansion about z is equal to 0. Okay, but here it contains negative powers of z. But whereas when you look at the Taylor series expansion, it contains only the positive powers of z minus z naught. So this expansion, namely f of z, is expanded in terms of z equal to 0, where z is equal to 0 is a singularity, but that expansion contains negative powers of z. So that is this type of series is called as the Lorentz series. Okay, and this expansion will be discussed in the next lecture. So what is the disadvantage in Taylor series? It cannot be expanded at about a point z is equal to z naught, when z naught is a singularity. But when z is equal to z naught is a singularity, we can expand the given function using the Lorentz series expansion. That we will discuss in the next lecture.